Hello, my name is Fola Shoyoye. I'm a lead product manager at iQuatic. I'm joined today by my colleague at iQuatic, Shui Yang, a data scientist, as well as Alina Petkova from our partner, John Snow Labs. Today, in our talk today, we'll cover an overview of risk adjustment. We'll talk about a solution that we built, some of the problems that we faced in terms of extracting clinical information, building a pipeline to extract clinical information from unstructured notes. We'll talk about why this is actually a problem today, and also go into a case study of computer-assisted coding. And I'll finally turn it over to Lina and Shui to provide a more detailed overview of the solution that we've put together today. To provide a high-level overview of risk adjustment, just to frame the problem space that we're working on. So risk adjustment is designed to help distribute payments to health plans in accordance to the health needs of their enrolled members. Essentially, risk adjustment payment models calculate the expected cost or risk for a patient and typically assigns an annual budget to a healthcare provider in accordance with that risk. This ensures that providers are able to work under budget and thus incentivized to not over provision or have inefficiencies that is typically prevalent in the current fee-for-service arrangement models. As healthcare evolves, more healthcare revenues are becoming risk-adjusted. And so Medicare, Medicaid, and private insurers are actually moving to paying healthcare providers on a risk-adjusted model. Hence, healthcare providers' revenue are being directly dependent on the risk assessment of their population. Health insurance risk assessment is traditionally based on data from claims data. Claims data in itself consists of previous services that were provided to a patient claimed through their insurance. Additionally, claims data, however, does have some significant shortcomings when it comes to predicting the true risk of a population. This results in, this essentially, typically we find that, claims data excludes about 40%, approximately 40% of risk-adjusted conditions, because those are not, the supporting information is just not recorded in, that are typically recorded in clinical notes are not found in claims data. So computer-assisted coding is one of the use cases here is one of the use cases of the risk adjustment program, which involves the identification of missed revenue opportunities in the form of misdiagnosis information that are found in clinical notes. Essentially, the goal of computer-assisted coding is to be able to establish a visit, determine a valid encounter, a doctor's visits within unstructured clinical notes. There are three criteria that help us establish a risk-adjusted valid visit. First, we want to confirm that there's a valid encounter that occurred, that there's a valid date of service that exists. We want to make sure that there's evidence of a face-to-face interaction between a patient and the provider. And lastly, we want to make sure that there's an acceptable signature that affirms the validity of the accreditation of the provider. There are certain, just like in an industry, there are problems that are, that currently exist that are faced with the risk-based contracts today. As I mentioned earlier, health insurance risk assessment traditionally is based on data from claims, and this leaves about 40% of risk-adjusted conditions unrecorded because the claims data that they're based on lack the clinical details that's necessary. The full severity of the conditions that is typically locked away in unstructured clinical notes are not being considered here. As a result of this, plans could actually lose up to 20% of revenue opportunities by not being able to extract that data. Second, the other thing here is that the coding process, the medical coding process, as illustrated in the computer-assisted coding use case slide deck, is heavily manually intensive. So it's heavily relied on people, on licensed professionals, combing through thousands of pages of medical records to find, to validate diagnosis code. And that ties into the last point here where, clinician notes are really not being reviewed because a lot of the technologies that exist today do not have the ability to go through clinical notes, which are often locked away in unstructured data sets. So we think that this is a problem that's primed for NLP because obviously there's significant volume of manual process going on, which is also error prone. And there are opportunities for introducing efficiencies here through automation with machine learning models. As I mentioned earlier, the process of computer-assisted coding, the process of medical coding is intensively manual. We're talking about reviewing thousands of pages of medical records, which could take several hours. And this is also based on skill, on highly skilled individuals. There are missed revenue opportunities. There are quality issues here that, if the accurate codes are not captured, they actually do lead they could lead to significant fines on the health plans or the provider side. Okay. So I want to talk a little bit about the Aquatic solution. Aquatic's industry-leading AI NLP technology and rich domain knowledge in the payer and provider community delivers superior healthcare IT solutions that reduce cost while providing improved analytics and clinical insights. Basically, what we do is the Aquatic platform takes in data from multiple sources, structured and unstructured, and particularly clinical data from disparate electronic health record systems. And we use that data to predict risk and cost of patient populations. We enable providers to price and manage risk as payments to providers transition away from fee-for-service. Providers are being increasingly expected to assume and effectively manage risk. So our focus is really on, helping those providers by providing a technology that supports them that supports mining data from electronic health records rather than just relying on claims data. We are unique today because our technology interprets EHR, including clinician notes, to understand what is being described by patients. As I mentioned previously, claims only covers half of the data that's present in EHRs. Interpreting the clinical rich data from EHRs allows us to identify the 40% of the conditions and severities that are usually typically missed by others. And we're also able to leverage algorithms that can detect near real-time developments avoid lags with claims. How did we solve this problem? We practically solved this problem in collaboration with John Snow Labs. We built a workflow that incorporates OCR, several pre and post processing to achieve structured text output, a combination of rules-based and machine learning-based document segmentation, and information extraction phases that's based on NLP. I'll go a little bit deeper into the workflow here. Because we're dealing with data in unstructured data sources, our process really starts at the OCR stage. So we've built a custom OCR with deep learning models that assist us in performing layout recognition and document analysis. We do this because we face a wide variety of different data formats in all the clinical records that we receive today. There are a couple of information extraction phases that leverage rules-based and machine learning-based Spark NLP pipelines, as I mentioned previously. In the first information extraction phase, what we do is the goal there is to actually identify what we call as a valid encounter from a scanned PDF files, as I mentioned earlier. So when we receive data, when we receive documents from clients, scanned PDFs, we run them through OCR text extraction, and the output of that we parse into several pages, leveraging document boundaries. Now, those several pages are grouped as encounters or visits. Not every encounter qualifies for risk adjustment, so we have to apply filtering to determine valid and invalid visits. For our computer-assisted coding use case, we only need to extract information in valid visits. So we apply filtering to decipher the visits that are going to be considered as valid and invalid, and send them downstream to the next information extraction phase that you see on the screen below. And in this information extraction phase, we're also leveraging NLP to perform a number of extractions, such as ICD diagnosis codes and other informations that we extract on behalf of our clients. At this point, I'd like to pass it over to Alina for her to go into some details on the information extractions phase, number 1, that you see at the top. Alina?
Thank you a lot, Fola. It was a great overview of a project. And my name is Alina, and I'm going to speak about today how we can use a Spark NLP library to solve the use case presented. So let's start. We're going to speak about... Just happened? So we're going to speak about information extraction pipeline, and we need that to make sure we identify documents correctly. So in our task, we have scanned documents with different pages in that. So they usually come in with PACs or with PDFs, just shared between the providers. And the first task is to identify where one document finished and where another starts. After we identify that, we will need to split the visits. So within every document, it can be a visit or not a visit, and when visit can be codable or uncodable. So to start with that, we first identified the blocks of information which could be useful for our process. So we did a lot of modeling here, feature extractions, and then we identified the main blocks which could affect the document splitting. So first block is PHA extraction, which is, in our case, going to be doctor information, patient information, and some contact data. So it can be a phone or address or maybe a hospital name. Then the second block is a document identifier model, which is a trained NER model with Spark NLP, where we see how what identifiers we have for our documents. And another block is a face-to-face model. In this model, we need to see if the patient was presented physically on the hospital, so if doctor saw the patient, or if it was just a consultation on phone, or it was maybe a request of the documents or something not related in requests for the medical documents. And then the last block is a signature detection. So in this block, we're identifying the signature of a provider, and we see if the signature is valid or not. Okay, so let's move on to PHI extraction block. In the PHI extraction and the identification, we want to make sure that first we're not exposing the sensitive data in the pipeline, and then the second, that we extract the important fields that we need. Let's talk a little bit about the general regulations about that. So as we know, in the HIPAA compliance, we should make sure that the patient information and sensitive entities like name, date of birthday, maybe medical IDs or some other references to the patients are not trackable. So if we cannot, and if we can identify it, then we have to obfuscate it. So this approach allows us to work with sensitive documents and share them to the providers which can see them. So in this case, when we annotate the documents, we first de-identify them, and when the all sensitive data was hidden from the annotators and as well as data scientists. And then on the second step, we could extract the same entities and add them as a feature to our document splitting. So here on the slide, I presented you how we can do it with just like 3 lines of code with Spark NLP. So we first need to load the embeddings we're going to use. We used clinical embeddings, which were trained on PubMed dataset. And then we used enriched the identification model. So this model allows us to select the entities. So the entities like a patient name, doctor name, address, they all will be detected there. And then with the identification model, we make sure we obfuscate them. So some features what we introduced recently to a Spark NLP library, it includes Faker. So it's the library to automatically generate random data like names, date, addresses. Then we also, with this project, could make sure that we improved the identification. So now we have extended list of names what we're using. We can de-identify upper cases, lower cases. We make sure that doctor and patient consistently de-identified through the documents, and we keep all the links. So next block I'm going to speak about is going to be training of the NER. Please, next slide. Okay, so here I'm going to speak about how we can train NER model with Spark NLP. So we used this model to extract the codable and uncodable documents. Well, it's entities we're going to extract from a model. So to train the model, we first need to form the core NLL file, and then we add it to the NERDL approach to train the model. So in this project, we faced a couple challenges that I'm going to speak about. So first of all, as we know, the documents coming from OCR. So it means we're going to have some OCR processing errors. So there are common errors like some symbols not identified correctly, or we're going to have some tables which is like scanned in the corrupted way. So when we're training our own NER model, we need to make sure that we have a proper pre-processing after the OCR. And in our case, it was another issue we faced. The data set was not balanced. So we have to manually balance the data set to have enough codable document identifiers. and then we train the model with that information. So we received some decent metrics on this model. So current metrics you can see on the slide, and well, there's still some ways to improve the model, and this could be done with a proper annotation. So when anytime when you're trying to train a new NER model, we recommend first to come up with proper annotation guidelines and then move to that. So in this project, it was successfully achieved, and it helped us to get this kind of results. So, and the last model in the pipeline one I'm going to speak about, it's how to train the customized classifier using the pre-trained BERT embeddings. Next slide, please. Okay, so we used that to train the face-to-face model, which was trained with Spark NLP and Spark ML. So in general, this model is about identifying if there is a patient was physically presented in the visit. So to do that, we first split the full data set to the sentences, and each sentence would identify if it contains the presence of a patient or not contains. And after, for the full documents, we grouped all the sentences, and if the document has any sentences we labeled as a physical presence, we label the full document as face-to-face document. To train this kind of model, we can use BERT embeddings, well, which can be replaced with some others. Here we choose to use a clinical pre-trained BERT embeddings provided by Spark OCR library. Sorry, not Spark OCR, Spark NLP. Here we used pre-trained BERT embeddings provided by Spark NLP library, and then we used a GBT classifier to identify the sentences containing the label of a physical presence. We received metrics. They're quite decent for this kind of problem because, as we know, the physical identification is something which can be gathered only from a context, and it's hard to extract it even for the manual annotators. So from that, I'm gonna handle to Shui, who's gonna present you a working example of our pipeline, and we're gonna see how it's all combined together. Shui?
Okay, thank you, Alina. So now let me show you a use case. So my name is Xueyang. I'm a data scientist at iQuatic. So as Alina already, as Fola already mentioned, so our goal is to help with the medical coder to confirm a valid encounter or extract the data of service, verify a face-to-face patient-provider encounter, as well as identify acceptable signature for performing provider. So the first goal here is to split a file to individual encounters. So here I'm showing is 2 pages PDF. That's from one patient, one PDF document, which has total 19 pages. So here it has only 2 pages here. So usually the page range we got from will come from like 1 page to thousands of pages. So after OCR, here we can see this is we converted the PDF files into text. And here is actually encounter boundary here, right here. So you can see the first part is come from the first page showing here, and the second part is from the second page. So this is a boundary we want to identify by our pipeline. So next slide, please. Yeah, so by using the model that Alina just mentioned, introduced, so we could successfully identify all the information, including signature, credential, using our signature detection model. And we extract the patient information server states using this PHI extraction model. And we also identified those document identifier those including like a type of the document or title and so on. So by using our customized document identifier, at last, we also extract those face-to-face information using our face-to-face NER model, face-to-face extraction model. So now we got all the features or say information listed in the right-hand side as the information that we could help us to classify and find the boundary for us to split the document. So next slide, please. Yeah. So here we can see we successfully find those boundary at the left up table. So we have those encounter and indicate the real boundary of this document, and we can find the docu boundary is predicted from the pipeline. So after some, we also have identifier filter, which indicate what kind of a document or we detect, and also we predict the signature, if this is a valid signature or not. In the prediction is we extract the face-to-face information to make sure this is a face-to-face visit from the patient to the doctors. So after we have those information here, now we go to extract our valid visits. So here is the results. We can see in this particular file with 19 pages, we have totally five encounters. In the 5 encounters, 4 of them is valid visits with all the criteria that are satisfied. So here we can see the beginning and the end of the document. We have the text extracted within this valid visits. So this will be the next step moving forward to other use cases. So here we can successfully kind of split the document and select the document that we are interested. So next, please. Yeah, so during the process, you can see we got a lot of challenge. For example, it's not very consistent, so it's hard for us to find a consistent pattern to determine the boundary. And we have multiple like different type of the files, and also annotation guidelines are not being strict. Like we have multiple document identifiers within a single document. It's not like it's only one in the document. And we also have like I mentioned, the various document format. It's not allowing a specific standardized format. So extract the information from also from like tables and columns format. And we also have like spelling errors from like OCR output. Sometimes we have OCR errors as well, like misinterpret characters, presented contextual challenges for us. And also at the last, the filtering valid invalid visits within the same document. It's also difficult. So next, please. So yeah, so in this collaboration with John Snow Lab, we can leverage those pre-trained model greatly speed up our development process. A lot of the challenges we're facing in previous slides. And also, we also have a problem like we have limited training data set. I think this probably a lot of use case will have the same problem. And as we know, the data labeling process is very time consuming and expensive. So those pre-trained models really helped us to quickly and doing a very efficient way to do our development. And also the Spark NLP enable us to build our customized NER models like Alina introduced. So we can use those NER model in this end-to-end pipeline and provide this and improve our overall performance. So moving forward, we are trying to boost the model performance by iteration of retraining with like more data in the future. Yeah, next. So thank you for attending this session, and we hope you enjoying our examples and experience. So we would like to take any questions and comments. Thank you.